I am going to be continuing the MDP discussion. Today we are doing the infinite horizon MDP value iteration and also policy iteration. It's actually the idea of policy iteration is actually more directly applicable for the infinite horizon ones because there's only the policy is not stage dependent, and so you can actually search in the space of policies. We'll look at that, and then we'll shift gears and look into stochastic shortest path algorithms, which is basically a special case of MDPs, and which are also close to automated planning applications. And depending on the time, we might look at labeled RTDP as an approach for stochastic shortest path algorithms, which is actually faster than normal value iteration idea. And then next class, mostly we'll be looking at factored MDPs. Assuming we didn't do all these things this class, next class we'll be looking at factored MDPs. And the papers that you are going to look at, FF Hub, you would be writing a review for FF Hub by next class, and also the other paper I sent, which is, I believe, I forgot the name, but it's the one which, what is the name of the other paper? That's the Kolobov-Weld paper. Those are the two that you're going to read, and those are like some of the examples of factored approaches for MDPs. So today we'll actually make the connection as to how we go from the classical MDPs to factored MDPs and faster atomic MDP algorithms. Before I go, are there any questions?
The reviews are due by next class?
The FF Hub at least will be due by next class. I will send an email on that. But I gave the papers last week, right? Yeah. At least one of them is due by next class. Okay. So, yeah, if in fact I do not complete anywhere near what I need to complete to get to factored MDPs next class, then I'll let you know, in which case we'll have the extra time for the reviews. Otherwise, it will be next class. So anyway, in the infinite horizon MDPs, basically we already talked about this fact that we need to discount the future reward, otherwise there is no way of explaining, there's no way of making sense of the accumulated reward from a given state because it will diverge. Okay. And we all talked about this. You want to think about it from the point of view of economics, or you want to think in terms of convenience of mathematics, psychological ideas, whether the later rewards are farther away. But so the discounting can be used also for finite horizon Markov-Daishing processes. Okay, so if you have a finite horizon, that's what we do. We know that we will actually be alive, we'll only live for like 100 years. And yet, if somebody is saying, would you like to have $10,000 today or $100,000 90 years from now, you actually make some sort of a deliberation as to deciding, whether $100,000 90 years from now what is it worth right now. Okay, so you could use discounting in finite as well as infinite horizon, but for infinite horizon it's required. Otherwise, you cannot actually talk about the value of a state. Okay. Okay, what else do we need to say? So, in terms of the evaluation of a policy, so if I were to give you a policy for infinite horizon MDP, then you can always convert the value for that policy. You can convert that policy into a value function, okay, with respect to that policy, and that's by this equation. So the value function with respect to pi for a state S is the reward of that state S plus, here he is using discount factor is beta instead of gamma. So beta times, you consider all the states as dash that you can go to when you do whatever the policy says you should do in this state in S, and then you get to go to S dash, and this is the probability of that happening. And if you do go to S dash, then you actually sample you get the value of that particular state. Okay. Now the interesting thing is this is a set of linear equations. This is a set of linear equations. Although it looks kind of ugly, it's actually, if you know, this is a number. I mean, it's a preset number beta, and these are all probabilities. So essentially, you will get equations of the type value function, value of S1 is let's say 0.1, which may be the reward of that state, plus 0.9, which is beta, times, let's say, if let's say my current policy says I should do action A in S1, and suppose if I do action A in S1 with 0.9, I get to S2, and 0.1 I get to S3. Okay, then I'll just basically say 0.9 times V of S2 plus 0.1 times V of S3. That's one equation now, right? And similarly, you can write an equation for V of S2, and similarly you can write an equation for V of S3. Let's assume that there are only 3 states in this MDP. Then essentially you have 3 linear equations with 3 unknowns. Okay, and then you can uniquely solve the values for those states. Okay, so value, policy evaluation. Policy evaluation is very simple. In fact, you use this. Where do you? I'm assuming that you all read this stuff. So in the policy iteration, you essentially keep evaluating the policy, convert the policy into the value, and value back into the policy. Okay, so this is the policy evaluation phase. So it's a linear equation essentially. So you can use any technique for solving linear equations. Okay. On the other hand, for computing the optimal value function, then that's more interesting, because then you have a max rather than a set of linear equations. So you get V star S is R of S plus beta. This much is fine, but now instead of the policy telling you which specific action you are supposed to do, you are considering all possible actions you can do. All possible actions you can do, and for each of those actions, you would get this. And then you have to take the max over all those actions, and whichever gives the highest, that is added to R of S to give you V star of S. So these two will give rise to a bunch of equations, except these equations will have a max term in the middle. So basically, you would say 0.9 times max of, and then you might say something like 0.1 times VS1, V star S1 plus 0.9 times V star S3, or 0.7 times V star S5 plus 0.3 times V star S6, let's say. Okay, so now you have this equation is really this plus 0.9 times max of this expression or this expression. Each of these expressions require the values for those states. Okay, so there is no obviously easy way to solve these equations. Okay, because of the nonlinearity of the max operator. And that's where we essentially notice that if you do value iteration, start from any value function and you keep iterating, you will converge to the V star. That's the theory part. That's the most interesting theory part of the infinite horizon MDPs. Okay, so the max operator makes the system nonlinear, so the problem is more difficult. So now, and also the optimum. So if you actually, this is basically the Bellman update. Okay, so if you could actually assume that each state has been given a value, and in the next iteration you reset the state's value using this. Okay, now if I know the current values of these states, then I can actually evaluate the max of this expression plus this and this expression, and then add that times 0.9 plus 0.1 will become the next iteration's value for state S1. Okay, so you're going to use Bellman backup as basically an update function, and if in fact there is an optimal value function, it better be the case that Bellman backup has a fixed point. Okay, you need to be able to show this actually, that there is a fixed point, and the theory as to why there is a fixed point is related to the fact that Bellman backup is a contraction operator on the value functions. Okay, so basically the Bellman backup is taking any value function, okay, v of s, and it's computing a new value function, okay, which is like this. Do you guys see that? So in fact, so instead of just thinking directly in terms of v star of s, let's assume that on these states s1 to sn, I am defining, multiple different value functions. If I give you one value function, that will basically for each state it will give you a value for that. Okay. Now, if I were to take that value function and apply the Bellman backup, I'll get a new value function. Okay. And the new value function would be like this, basically, because this is what Bellman backup is doing. It's taking each state, and another thing to do is you have to realize that essentially what Bellman backup is doing is to make everybody consistent with their neighbors. Okay, how many of you actually played with that applet that I sent? Okay, if this is a graduate course, you can listen to me and then you can go home, but if you don't actually open, there's only one guy who can raise their hand. If you don't actually spend time on the site, then don't expect miracles. Okay, so one of the points of that applet, basically, if you notice, you would now notice that if you played with that applet, you would notice that the values of the states close to the trap states will start converging first, and then so even though you have wrong values all over the place, slowly everybody looks around each other, around their neighborhoods, where the neighborhoods is defined in terms of the best actions they can do from themselves, and then they make their current value consistent with their neighbors' previous values. Okay, and so Bellman backup essentially is just one consistency operation. Okay, and one more consistency operation, and if you keep doing this consistency operation multiple times, then you get a fixed point. And to show that there is actually a fixed point, all you need to show is Bellman operator is a contraction operator. That means if you give two value functions, the distance between those two value functions will reduce if you once apply Bellman operator to both of them. So in particular, BV minus BV dash is less than or equal to V minus V dash. Okay, and in particular you can actually show it's less than or equal to beta times V minus V dash. Okay, every time you do this Bellman update, the value functions are coming closer. Okay, and if that is the case, if it's a contraction operator, then ultimately the contraction will stop at the fixed point. Okay, and it stops essentially at V star, and in fact, if there is more than one fixed point, then it cannot be a contraction operator, because then depending on where you start, it's going to end in different places. Okay, and the other thing, of course, is if you do have a fixed point, then applying Bellman operator to any starting value function. So here is the interesting thing. Suppose if I say V star minus V, okay, V is my current initial value function, and V star is the unknown optimal value function. Now if I were to apply B to V star minus B to V, now B to V star is Bellman update on the fixed point. It's the same as V star. Okay, so V star minus BV. Okay, and this will be less than or equal to gamma times, beta times V star minus V. Whenever I put minus V star minus V, I'm talking about the distance between the two value functions, and we use max norm. You know, if I have a value function is a vector, right? You have states S1 to Sn, and the value function is a vector on these states. It's an n-dimensional vector. And given two vectors, the difference between them is the difference across any given, the maximum difference across any one of the dimensions. Okay. Okay. So value iteration starts with pretty much anything. You can start with V star S. You can essentially actually set V star S to 0, and VKS is the previous value function from the VK minus 1S with the Bellman update on top. Okay. Now notice that V0S doesn't have to be set to 0. It does not have to be set to 0. It can be set to a slightly better value, which is correct, actually, which you believe is closer to V star. And you will notice that most of the applications of these ideas in planning will come from using some relaxation analysis to compute an estimate for V star and set that up as the initial value, and then do the value iteration. That way you will take much fewer iterations before converging. Okay, and so why does this converge? It converges, as I said, because of the contraction property. Okay, and so in particular, you can show this. And let me actually, the book in the normal text part of the book, it doesn't explain why it is a contraction operator, but there is actually an exercise. If you have looked at it, it tells you how to go about showing that Bellman update is a contraction operator. Let me just show you that, so that you have an idea as to how to do it. This is more of a proof sketch, but it corresponds to a particular problem in the exercises of that chapter. And to do this, basically you start with a simple point that if I have two functions, f and g, then that holds. Okay. So suppose I have f is like this. Okay. Suppose I have f like that, and I have g like this. Okay. Right. Now, what this is saying is max over f, fa, minus max over g, ga. This distance, this difference is smaller than or equal to the maximum difference between f and g at any point. Right? Not too hard to see. You should be able to prove it too, but it's actually not, it's intuitively, it makes complete sense. Okay? Right? And once you start with that, once you agree with that, then you can show that the Bellman update over V minus Bellman update over V dash is less than or equal to beta times V minus V dash. And the steps on that is to write Bellman update for state S, let's say, which would be R of S plus beta times the usual thing. Okay, and similarly Bellman updates for V dash, it's a different value function and the same states though. Notice that just because the value function changed, all you changed is the value function, nothing else has changed. The actions remain the same, that means the transition functions remain the same, the reward function remains the same, the neighborhood remains the same, everything else remains the same. It's just that I said here is value V1 and here is value V2 over the same space, and Bellman operator uses the structure of the transitions and the structure of the reward function to compute the next value function given a value function. Okay, so for B of V, it would say this is the updated one, and for V dash, it will say this is the updated one. Notice that the V dash is written in terms of V dash, V is written in terms of V. Now if I take the subtract, if you subtract one from the other, then basically it's b of v minus b of v dash of s is, now this and this cancels out. Notice I can do this because underlying MDP hasn't changed. It's the same exact reward function. So this cancels out, and then I have essentially beta times max of this whole thing minus max of this whole thing. That's like max over one function minus max over another function. Okay, which can then be written as max, which is less than or equal to max over all values, all the differences between those two functions. Okay, so that's what I'll say is this whole thing is less than or equal to beta times max is taken outside, and then this whole thing minus this whole thing. Okay, so that's essentially what you're doing. And notice that this part essentially, ultimately it's just vs dash minus v dash s dash, because the transition probabilities are also exactly the same ones that both updates will use, because transition probabilities did not change. Right? What you could do from this particular state, s doesn't depend on v or v dash. It only depends on what action, what is the transition function from that state to all the other states that you can get to using these actions. Okay, so that's basically the idea of how you show that contraction occurs. Okay, so you're able to essentially see that the Bellman update over two value function reduces their distance. Okay, and then eventually, in particular, that this also means that v star minus v of v for any initial value function v will be less after one iteration. So it's less than or equal to beta times v star minus v. And so all that matters now is beta should be strictly less than 1. As soon as it's strictly less than 1, then you know that after a bunch of iterations, this is going to reduce to 0. Okay, how fast it reduces depends on how low the beta value is. That's the other thing that you could actually play with that applet and figure out. In fact, one of the things you do in that MDP applet is you get to change the discount factor. And once you change the discount factor, one of the interesting things is that if the discount factor is extremely small, in fact, if the discount factor is 0, then how long does it take for the value function to converge? Once, because R of S is the V star if discount factor is 0. Okay, whereas if the discount factor is extremely close to 1, then it takes forever to converge. Okay, and that's something that you can see, and that's also actually you can make sense of from these bounds. Okay, in particular, given you know that v star minus the v star minus v of v is beta times v star minus v, right? And so if I use the notation b power n to mean applying Bellman update n times, right? Then using that same thing, I can say v star minus b power n v would be less than or equal to beta power n v star minus v. Okay, now what I might want to do is to stop iteration when my current value function is only epsilon away from the optimal value function. So that is basically v star minus v. Okay, so if that is less than epsilon, that has to be epsilon, then you can see how many times you have to actually update to get to that value. You take logarithms on both sides and do some algebra, and you'll get, a bound on the number of iterations that you need to do, so that the bound on the number of iterations you need to do so that you would get convergence. I mean, you will get up to epsilon, within the epsilon of the V star. And that bound will depend, will nicely have, a factor like 1 minus beta in the denominator, okay, which will become infinity if beta is equal to 1. Okay, that basically the textbook has this whole thing set up. Okay. And in fact, the textbook also points out that that bound tends to be kind of a very pessimistic bound. It's a good way to prove theorems, but it tends to be a pessimistic bound, and in fact, you might actually converge much faster than what that bound says. That bound says you need to do, by these many iterations, you will certainly be within epsilon of V star. But you might actually be within epsilon much before that. And so, the way you actually write the value iteration is not just blindly do the bound number of iterations, but rather compare the value from one iteration to another iteration, taking the norm and seeing when the norm becomes less than epsilon. And if two value functions are, epsilon away from each other, then you can actually show that they are also close enough to V star. That the last one is close enough to V star. Okay. Now, in terms of value iteration, so you would stop after the value functions between two iterations are close enough. Okay. And then at that point of time, and in fact you can stop anywhere during this number of iterations. You could have done like 100 iterations and stopped. And if you stopped after 100 iterations, let's say you will have a value function. Then if they say you don't have any more time to think. One of the interesting things about Markov iteration processes is the value function, computing the optimal value function is like doing planning. That's what you're thinking of. If you know the optimal value function, then you know what is the optimal thing to do from the current state. Because you know the value function, you can convert it into the policy. If you don't have the optimal value function, I stopped you, I interrupted you before you got done. Okay, then you have a value function right now. You can convert that into a policy. That's called the greedy policy. That's basically assuming that this value function, which you're not sure is the optimal value function, you act as if it is the optimal value function. Okay, and if I give you that as the value function, then the greedy policy is basically to do from each state the action that maximizes this. Right? Okay, so all I know is currently I have an estimate of value of every one of the states. Okay, and now I'm in a particular state S1, I can do action A or B or C. If I do action A, this is the expected value I get. And I do B, I'll get a different expected value. C, I'll get a different expected value. I just do the max of those. So pick the action that has the max. Okay, so this is basically inverting the value to policy. This is exactly what you do after you computed the V star. If you did compute the V star, the same exact idea will give you the optimal policy function pi star. Okay, however, while V star and pi star are related, at the optimal function, V star and pi star are related. That means you start from pi star, you'll get V star, and if you start from V star, you get pi star. Right? Again, what do I mean by starting from pi star, I'll get V star? Because if a couple of slides back, I pointed out to you how to evaluate the policy. If I give you a policy, you can compute a value function corresponding to that policy, solving a bunch of linear equations. That is going from pi star to V star. Okay, and then similarly, if you are at V star, you can go to pi star using this method, which is doing greedy optimal action. Normally, when V and pi have not reached their optimum values, these two things don't necessarily converge. So for example, the funny thing is if I have some V, K, and if I actually do the greedy, I'll get some pi K. And if I were to evaluate phi k, I don't necessarily get Vk, I'll get some Vk dash. Okay, this may look like a bug, but this is actually the rock climbing that you use to do policy iteration as against value iteration. Because when you change the policy, the value, when you change the policy from one place to another place, you're getting a better value. Okay, these two will actually be the same when v and pi become optimal. Before they become optimal, if you take a value function and find the greedy policy corresponding to that, and then you evaluate that policy, you get a value function that's different. But that is also going to be close enough to the V star. Okay, so in particular, so let's look at this. So in particular, if I'm ever stuck with any value function and I don't know whether or not it's optimal, the best I can do is do the greedy policy. Okay, now, so let Vg be the value of the greedy policy. Okay, you started from Vk to get a policy, and then you evaluated that policy to get Vg. Vg and Vk are not necessarily the same. Okay, unless they're, unless V is already optimal and pi is already optimal, Vg and Vk are not necessarily the same. Okay, however, we can show that greedy is not too far from optimal if Vk is close to V star. That means if Vk was close enough to the optimal policy, unbeknownst to you, if it was within epsilon of V star, then the greedy value function would only be this far away from the optimal value function. Okay, and so to get you a feel for it, if unbeknownst to you, the Vk was 0.001 away from V star. Okay, and then you convert it into an optimal, and then beta is 0.9, then you can be sure that doing the greedy policy will get you a greedy value function that's like 0.018 away from optimal. Okay, so it's also close enough to the optimal value function. Okay, notice that you won't know this beforehand. You don't know when you stop at a particular point exactly how far away you are from V star. You only know how far away you are from the previous iteration. Right? And okay, so the other interesting point, so that's one thing, so doing greedy is actually okay. And what's more interesting is that there will be a small epsilon such that when Vk has come within epsilon of V star, so Vk is not the same as V star yet. And if you were to compute the greedy policy with respect to Vk, that would be the same as pi star. Did you understand what I'm saying? So all we normally know is that if you were at V star and you do greedy, you will get pi star. What we are saying is, even if you are at Vk, such that Vk and V star is only epsilon away, for some small epsilon, then Vk's greedy can also be pi star. So that's your opportunity. So that means if you are close enough in terms of value, then the policy would already be optimal. And in fact, this is possible actually partly because policy function is discrete. Value function is continuous. Right? And so all we are saying is there is some sort of a unit sphere, unit hypersphere around the optimal policy vector, such that a value vector anywhere in that sphere will still get you to the same policy. Right? Because there are infinite number of value functions and finite number of policy functions, it has to be the case that regions of value functions have to be mapped to a single policy function. This is a no-brainer. Otherwise you couldn't have done it. Okay? And all we are saying actually is that that can be used. In fact, there will be a small enough region around V star such that that V star's greedy function, that in that region, any value function in that region would have already the optimal policy. So what that means is, if you are just doing value iteration and you stopped only when epsilon became 0, you had infinite amount of time and you stopped only when epsilon became 0, and then converted the policy from V star to pi star. And if you were also doing this on the way to see what is the intermediate policies, you would have seen that your optimal policy converged much before optimal value converged. Okay? And this essentially gets you to take policy iteration into consideration, because to the extent policies converge faster than values, why search in the space of values to begin with? That's what policy iteration is. Yes, sir?
So then, can you determine that a policy is optimal by if you take this value function and compute the optimal policy for that, and then take the value function, the two value functions match, then the function is optimal?
So you are essentially saying, so if you have, yeah, that's more or less what policy iteration does, right? Okay, that's more or less what policy iteration does. Okay, so we basically at this place I'm actually sort of going to get out of value iteration. Okay, although we will come back to it multiple times later on. Even though we will talk about policy iteration in the next slide, you would be surprised to see that most of the papers that we read about applications of MDPs to planning will still depend on value iteration rather than policy iteration. Okay, for reasons that will sort of become slowly clear to you. But you are essentially taking this epsilon gap to converge to the policy faster. And what it's saying is, given a fixed policy, we can compute its value exactly. Policy iteration exploits this. It iterates the steps of policy evaluation and policy improvement. So choose a random policy. Instead of choosing, in the value iteration, you choose a random value and you start iterating over the value. Here, you choose a random policy. Start from initial policy. And then loop. First evaluate the policy to get the current value function with respect to that policy. Okay? And then for each, and then once I got the value function, now I convert that value function into a new policy. Normally it looks like it's a cycle, right? I started from policy, you got to value, and then put the value back to policy. It should be the same as the old policy. However, that will only be true if in fact the policy is already optimal. Okay? Otherwise, you will actually get to a better VG. So this is basically, you started with a policy, you got a value, and with respect to that value function, you are computing the greedy policy, pi dash s. Now, if pi dash and pi are the same, you stop. Okay? If pi dash and pi are not the same, then you say pi dash is pi. The new policy replaces the old policy, and you start the loop again. That's it. Okay. Now, of course, the tricky part is evaluating V pi essentially involves running a set of linear equations to solve the actual values corresponding to this policy. Okay. So that's the classical policy iteration algorithm. Okay. Now, what's interesting is that you can actually combine policy iteration and value iteration in the following way. Suppose you don't really want to spend too much time evaluating the policy. What I could do is, this evaluation of the policy can be a call to a value iteration algorithm for some fixed number of iterations. Remember, value iteration algorithm normally assumes Bellman update. Now, if you call it with a single policy, it is even happier. Right? So what it's basically doing, this is, in fact, I find most of this stuff, the value iteration in particular, I find the spreadsheet metaphor very compelling. Okay, in spreadsheets, basically, you have values in different cells, and you put constraints between these cells. Okay, when the spreadsheet is consistent, then all the values in all the cells are consistent, are obeying their constraints. Now, rather than look for the consistent state, which is sort of the V star of the spreadsheet, you can also say, I have a random spreadsheet right now, let me make it a little more consistent. Little more consistent by look around myself and see if there are any constraints I'm supposed to satisfy with respect to the other guys. If so, let me push myself slightly more towards those constraints. If I keep doing this, then eventually, I can get to the V star. And this is also kind of like the way we tend to clean our rooms. Most of the men at any rate. It's like, there's an optimal configuration of the room where everything is clean, but then you go into the room, everything is fallen all over the place, and then you say, yeah, if things are right, then the books are probably supposed to be stacked. So I stack the books. Now the rest of the room is still pretty bad, but locally the books at least are slightly more consistent. Bellman update is making things consistent, with respect to the neighborhood. Okay, and the policy, if I give you the policy, then I'm just becoming consistent with the neighborhood with respect to that policy. Okay, if I do k number of iterations of the policy update, value iteration for given the policy, then I can then use that new value function as the basis to do this. It turns out policy iteration with that idea also works. Do you understand what I'm saying? So if you don't feel like fully exactly evaluating VPI, instead of evaluating VPI, you call value iteration for only a few iterations, whatever you feel like. And then it will give you a slightly better value function that's more consistent with this policy. And then I make that part of this. Okay? And that also works. That's a better value policy iteration than the normal policy iteration. Since I gave you policy iteration and right away told you how to improve it, okay, I should also tell you how you could, the many different ways in which you could have improved actually value iteration. Okay, in fact, we'll spend a lot of time in today's class and the next class too on that, but let's first say at least one thing. The way the value iteration has been mentioned to you, it's sort of a synchronous update. So you start with V0s, update all the states in V0s such that you get V1s, update all the states, you get V2s, update all the states, you get V3s, and then you start with V star s. Okay, and moreover, when you are computing V1s, you only look at the values of the states from V0 iteration. When you look at V2s, you only look at values of the states from V1 iteration. That's why it's called synchronous iteration. There's like a clock taking V1 to V0, so V0 to V1 to V2 to V3. It turns out, while that is a way you can think of to understand the contraction idea, it turns out that actually you don't need to do that. In fact, suppose it turned out that you started with V0 and a whole bunch of your neighbors have already updated their values. So they're already in the V1. Now when your turn comes to update your value, why should you not use your neighbors' V1 values? Why do you have to use their V0 values? In fact, if you use their V1 values, presumably V1s are better than V0s, right? So if you use your neighbors' V1 values, you will get a better approximation to your eventual V star. Did you understand what I'm saying? And if you do this, the iteration actually converges much faster. The value iteration converges much faster. And this is essentially called asynchronous value iteration. This is called asynchronous value iteration. Okay, now once I do asynchronous value iteration, there's the other thing. If I don't have to be synchronous, I don't have to take everybody from one iteration to another iteration, then I can also say some guys don't even need to be updated for a bunch of iterations. Only the important people get updated more often. and the less important states get updated less often. Okay, that's called prioritized sweeping. Okay, this is a nice idea, the name for it, called prioritized sweeping, where some states are updated more often than the other states. Some states are updated up front, then the other states are updated later on. And it turns out that you can, in all these ideas, if you are into actually making sure that the theorems will hold, that the fixed point theorems will hold, you need to reprove the theorem with prioritized sweeping, with asynchronous iteration. Intuitively, you could see why these would work, and actually, if you get Peterman's book on mark rotation processes, he proves all of these separately. Okay, and in particular, prioritized sweeping will get you to the optimal value function as long as every state does get updated infinitely often. Even if it doesn't get updated for 100 years and then gets updated lots and lots of times, okay, that's good enough. All you care about is will you have an asymptotic convergence? An asymptotic convergence will hold as long as everybody has non-zero probability of being updated. Okay? Okay? Now the other interesting question is, why is prioritized sweeping actually a much more reasonable thing to do than what MDP was doing? The normal, can you think of a reason as to why you would want to do prioritized sweeping rather than normal, everybody gets updated to the next level kind of an idea? Suppose the domain is not very stochastic. What do you mean not very stochastic? Suppose the domain is such that for each action there is a 0.99 outcome and a 0.01 outcome. That's it. Every action has exactly 2 outcomes, and there is a 0.99 outcome, there is a 0.01 outcome. Which essentially means that there is a very high expectation trajectory in which things are supposed to happen. And there is also a small low probability that things will go haywire. Okay, now which states do you, if you don't expect to be doing the value iteration until the end of time, and anybody can stop you at any time and say, tell me what you're going to do now. Okay, then you are better off knowing what is the right thing to do. You're better off knowing what is the right thing to do in the more likely states than the less likely states. Of course, you may still have less likely states happen. So the idea is, you did an action, okay, and by probabilities, the 0.99 effect of that action is going to happen. So before they come and tell you what is the new state and ask you for the action again, if you're going to spend your time, you might as well find out, what you should be doing in the more likely state that comes from doing action A in this status. Okay, so prioritized sweeping gives you optimal, it will make sure that the value function converges in the reachable parts, the high probability states, much before it converges in the low probability states. So this is like saying, when I'm going off to San Francisco, I would just make sure that I know the right thing to do if I do actually get to the airport, if I do actually land in San Francisco, if I do actually stand in front of the taxi domain, in a taxi stand. Okay, but well, obviously I should also know what happens if the flight falls down right in the middle of the Arizona desert. Right, that's possible, and I should know what's the optimal thing to do. Right, for example, perhaps I could just take rest under the, what are those things called, what trees are those? The Joshua trees, and wait for. By the way, Joshua trees actually don't give much of a shade. I had a friend who once was driving from LA to Phoenix, and she was from East, and she thought that she'll stop by in Joshua Tree National Forest and National Monument, which falls in the Mojave Desert, and have a picnic under the Joshua trees. She thought it's a tree, there'll be a lot of, nice this thing. But anyway, so you may not quite know what's the right thing to do, I mean, I want to make sure I know the optimal action to do when I get to the, when the plan actually occurs in the way I expect it to occur. Okay, it's kind of less rational to know that if I do fall in the desert, the right thing to do is to have the right kind of, whatever, the wireless equipment to tell people that I'm stuck in the desert, and not know what to do if you actually get to the taxi stand. Do you understand what I'm saying? That's what happens if you don't plan. I mean, you go to the taxi stand and say, what am I supposed to do now? Well, that would basically be much more irrational, because you know what to do in the unlikely states and not what to do in the more likely states. Prioritized sweeping could make sure that you know what to do in the more likely states. Okay? Now, by the way, whatever I did in MDPs till now, so value iteration, policy iteration, and the variations on the value iterations and variations on policy iteration, you could do this as a semester-long course just by itself, and proving everything I said. Okay? So you can get a feel for, we're just basically shifting over the atomic model fast so that we can go to the more efficient approaches. But all of these, you can actually spend your time trying to prove that these make sense. And for the longest time, these very simple ideas like prioritized sweeping were like a big deal, because people weren't even sure that they can prove that they will converge. Okay? I'm sorry. Okay, so if you're comparing policy and value iteration, one interesting point is, of course, policy iteration takes much fewer iterations because there are only a finite number of policies. It cannot do more than a power s number of iterations, because there are only a power s number of different policies to begin with. Whereas value iteration can do infinite number of iterations because there are infinite number of policy functions, value functions. Okay. However, the problem with the policy iteration is per node, per iteration cost is extremely high. It's solving these linear equations basically. Now you might just think, oh, it looked like in my example there were 3 states and 3 equations in 3 states. That was easy. But normally, suppose I have k propositions in the factored representation, then I have 2 power k states, and I have 2 power k simultaneous equations, linear simultaneous equations. And you can go crazy solving all of them. I mean, you'll have huge matrices, and in fact, the stuff that you would have heard of, in fact it's said here too, when we looked at computing the policy. Evaluating the policy, use linear algebra, just do matrix inversion. Matrix inversion with k equal to 100. So 2 power 100 equations isn't something that you would suggest to your friends. Okay, right? Your enemies maybe. Okay. So the point is that it's a pretty costly, again, the other thing that I mentioned last time is MDPs originally were solved with the number of states being tens of states. So, in the OR community, MDPs are solved for tens of states. Okay, where you ensure that the problem that you have becomes abstracted correctly enough such that you're only considering tens of states. Okay, whereas when you do it in planning or in AI in general, the assumption is that you allow, you don't want to intercede and do all the abstraction yourself. You want the system to be able to deal with any representation that's given to you. In which case, you might give a large number of irrelevant variables in the state that describe the state. So 100 state features is not out of the ordinary, which will then give you 2 power 100 states. And in general, in OR, basically, if you open a standard textbook in operations research, they would be able to show how to solve a MDP on the page itself. They take a small enough MDP and you can show how to solve it and with pencil and paper. We don't expect to be able to do that. It's the scale that matters ultimately. Okay, so some of these ideas just basically fail when you're talking about 2 power 100 states or 2 power 15 states. And so you need to think of efficiency. Okay. So anyway, in terms of policy versus value iteration, policy iteration has a fewer number of iterations, but each iteration is extremely costly. Value iteration, you don't know how many iterations it will do, but each iteration is quite cheap. Okay, and furthermore, if you throw in things like prioritized sweeping, you can decide to only update the values of states that are actually likely to be encountered with high probability. And then if they say you're done, okay, you have to start acting now, then you have something to act with. Whereas if you're doing a policy iteration over a 2 power 100 MDP, you haven't even completed the first iteration because you're still setting laboriously the 2 power 100 equations in 2 power 100 unknowns and getting the floating point and memory overflow errors. And they say, what's your action now? And you can say, no, if you give me only some more time, I'll tell you the exact action, but you're dead by that time. Okay? So this is actually the reason why many of the things that we'll see later on, including the papers you are reading, they all deal with value iteration rather than policy iteration. Even though in the textbook it looks as if policy iteration is such a smart idea, because it's just fewer iterations, and there's a bound on the number of iterations. Okay? So it's the computational trade-off is something that you want to understand. Okay. This is the value iteration versus policy iteration. Okay, so that's on the classical MDP approaches, and I'm going to now shift over to combining these to planning. Okay, remember that MDPs are atomic models. They are much more expressive atomic model than A-star search, right? Because they allow stochastic actions, they allow generalized reward functions. Okay, that's all well and good. However, it is also the case that you didn't even solve planning problems by converting everything into pure atomic model and doing A-star search. So you're just certainly not going to do that in a more expressive model. So the rest of the action completely is about what can we do to make value iteration work faster. I mean, in fact, you could say value or policy iteration, but mostly value iteration, because that lends itself to all sorts of cutting corners. Okay? But before we go forward, let me just say that there are many MDP models. And in fact, one of the interesting things is that the general model that we have looked at, the infinite horizon MDP and finite horizon MDP, those are just two of the classes. But if you understand the theory of them, there are other variations that may actually be more relevant to us. In particular, so this is what we looked at, infinite horizon discounted reward maximization MDP. This is what we looked at. Okay. Now, if you think of, let's say, deterministic planning, okay, it's not very obvious why this is directly out of the box relevant to deterministic planning. Because after all, deterministic planning is supposed to be a special case of Markov-Ratian processes. Okay, and yet, in deterministic planning, you never give anybody any reward. You only actually incur costs. Right? It's like it's one of these things where the beatings will stop and the morale improves, kind of a thing. So when you reach the goal, we'll stop hitting you. Okay, but when you reach the goal, you don't get anything. You just stop getting hit. That's what the MDP model is. Okay, so the view of maximizing something just runs contrary to deterministic planning, where you are minimizing the pain. Do you understand what I'm saying? So normally we tend to use the opposite. Basically, instead of thinking in terms of value function, we think in terms of cost function. And just as you tend to think of V star, which is the optimal value function, you can define J star, which is the optimal cost function. Okay, and what do you think the Bellman updates can be written for those too? Bellman updates would no longer have max, they will have min, right? So it's essentially this model, so goal-directed, indefinite horizon, cost minimization MDP, is the model that is actually closest to classical planning, deterministic planning, which is where we are coming here. Okay, so for getting all the goals done, you don't get any pats on the back. It's just that when you get all the goals done, the pain stops. Okay, and you win by minimizing the amount of accumulated pain, accumulated cost. Right? Okay, so that's a different model, and it's like it has normally from model to model. What changes is the Bellman equations will have a slightly different format. Okay, the reason I'm bringing this up, so this is what you have seen with infinite horizon, and the finite horizon case of this also is what you have seen. I will show you the Bellman update equations for this, but you can also talk about a slightly different version. For example, goal-directed finite horizon probability maximization MDP, where suppose actions don't have costs. Okay, all that matters is you want to increase the probability that you will get done in soon. You get done soon by reaching all the goals. Okay, in fact, the probabilistic planning competition that we will talk about later on, maybe next class or something, actually looks at this problem. So what they do is, the way they set it up is, the way they set it up is, they will tell you what the current state is, you tell them what action you want to take, they will then do the action in the real world or on their simulator, and will tell you what the state is, and then you tell them what's the action to do. And if you ever, by doing this, if you ever reach the goal state, they'll say, hey, you won. If you reach a trap state where you die, they'll say you're dead. If you don't reach a trap state, but the amount of time taken, basically exceeded, then you still haven't won. You have not reached the goal state. Okay, and the probabilistic planning competition is set up in such a way that everybody is given, like, I think 30 minutes. Every planner is given 30 minutes. The same problem, they know the exact transition matrix. That means, given the state, what are the probabilities of reaching, if you do this action, what are the probabilities of reaching various other states. Everybody knows the same exact knowledge. Everybody is given the initial state of the problem, and then everybody is asked, okay, what's your action? And they'll tell you, they'll think a bit, and they'll give an action. Okay, and then the simulator does the action, comes back and tells the planner, here is your new state, tell me what to do. And then you give a new state. And as soon as you reach a state where all the goals are satisfied, then you win, you're done. And the other guys can still continue because they are not done yet. And a planner is better if, for example, it solved most problems. And then because it's a stochastic dynamics, for each single problem they do at least 100 tries. Do you understand what I'm saying? Because it's not deterministic. So when you do an action, sometimes it goes the way you would expect, and sometimes it goes a different way. So for example, if I'm a solver which actually, think about that, the San Francisco scenario, right? The guy who knows exactly what to do in the airport and in the taxi stand tends to win most of the time fast, but would fail pretty miserably if in fact the flight drops dead in the middle of the Mojave Desert, because they haven't gotten around to figuring out what to do there. In those cases, they just die. Okay? Now, over 100 different trials, they might wind up winning maybe 70 of them, like maybe, hopefully, since we are still flying, hopefully 99 of them, and die badly in one of them. Okay? Whereas somebody who is so smart that does both the optimal policy for the more likely states and the optimal policy for the less likely states will win all 100 times. And so that planner legitimately wins. And the planner which will definitely die is the one which decides to put all its energies to figuring out what should it do if it were to fall down in Mojave Desert. Because the one time when it does fall down in Mojave Desert, it knows exactly what to do, but the other 99 times it's just randomly doing an action. Okay, so those are the trade-offs. Okay, and you know, a planner is basically first considered in terms of the how many times has it reached the goal state. So the number of times you reach the goal state by the total number of times the problem is run is the probability that you reach the goal state. And you are trying to optimize the probability. You're trying to do your actions such that the probability of reaching the goal state is maximized. So here you have the value function, here you have the cost function j, and here you have neither value nor cost, you only have a probability function. Okay, and what do you think the Bellman update would look like in the probability function? In the value function you add values. You basically add the values, probability times the value plus the next probability times the next value. In probability maximization it will be a big multiplication. Okay, so let me show you those, and then this is actually a slightly different one. I won't talk about it right now. Oversubscription planning, which I haven't explained to you well enough, you don't realize the subtleties in this, so we won't talk about this right now. Okay, let's look at Bellman equations for the cost minimization MDP. I'm going to show these to you by the end of the class, and then you should go back and look at them and make sure that although they look different from the equations I showed in the previous slides, they are essentially the same. In one case you're doing minimization instead of maximization, for example. So here you think in terms of J star instead of V star, and you assume that J star, let's say S is equal to 0 if S is G. The state is a goal state, then the J star value of that state is 0. Okay? If otherwise J star value of a state is defined in terms of its neighbors' J star values. Okay? Now, if you are in S, you do an action A, you get to S dash. Okay? And the probability of that, the cost of doing that transition, this is in essence like cost of action A, plus the cost that you will incur from S dash itself. Notice that all the sunny verbiage of the unlimited possibilities of a state being, being encapsulated in its value function are replaced by the non-sunny version of unlimited pain that you can get by being in this state. Okay, so J star S is if you start here and you do the optimal things, you will get only this much pain, not more. Okay, plus to get to this from S, you did this action, so there is a cost for that. Okay, and now the probability that this will happen is based on doing A in S, you will get to S dash. There is a probability. This is the transition model. This is the cost model of the actions. This is the transition model. This stuff is what you are trying to compute. Do you understand what I am saying? So these numbers are given as part of the problem. This is what you are trying to compute. Okay? Now this whole thing, by the way, there is a name for it. It's basically called the Q value of doing an action A in state S. And we'll talk about why Q values are quite important in reinforcement learning. But think of right now this as just a shorthand notation for that underlying big expression. What happens in reinforcement learning is you don't know this, because you don't actually know when you do an action what state you will reach with what probability. In reinforcement learning, you cannot simulate in your head because you don't have the model of the world. Instead, you do it. Like the kid putting its hand on the red hot stove and see what happens. Okay? And the interesting thing is, if you think in terms of only Q values, you don't need this. Q value is directly experienced. Right? I did putting hand on red thing from the current state. And how much pain did I get? That's my Q value for doing that action from that state. Okay? And now basically if a kid, is standing in front of it, there is a red stove, there is a candy, a plate of candy, and there is like, mind-numbing TV show, it could do any of these 3 actions, right? It does all 3, figures out what works out, And then hopefully if the kid were to live for one more day, they would have done some thinking and say next time around let's eat candy. Okay, this putting on the stove is not working out well for us. Okay, and so it minimizes over the action possibilities, the overall pain it got. Accumulated reward gets changed to accumulated cost. Okay, that's it. That's your J star S. This is your Bellman update equations, right? Bellman equations right now. Now I can do value update, value iteration and policy iteration in these two. Instead of value iteration, it becomes cost iteration. Okay? Right? Okay, and then the interesting thing is, if this is sort of what you will have in mind most of the time, because remember things like heuristics. Heuristics are supposed to be the lower bound on the true cost. If you want to think of heuristics in terms of value functions, heuristics should be upper bounds on the value you can get. Right? Okay? So, in fact, in the cost model, heuristics will basically, if you want to talk about, can I start with J0S as a lower, with a good heuristic initialization of the cost function, cost to go function, okay? I would, if I have H star, for example, that would be J star. Right? So this model directly corresponds to planning. If these probabilities are such that they are ones and zeros, then you have a deterministic model. Okay? And then J star would be equal to H star. And if you want to get H star by, and so if you want to get H star by starting with some reasonable H, then you need to get a lower bound H. So similarly, when you want to come up with optimal J, and you want to start with an admissible initial value for J, you come up with an admissible heuristic and say that's my cost, and then do the iteration. Okay? That's for that. Now, this you already know. This is the Bellman equation for the reward maximization MDP. There you do max instead of min. Okay, this one is nice because I told you about the probability maximization, which is actually what the probability, this is actually what the probabilistic planning competition cares about. And so what do you do here? So P star should satisfy basically, P star ST is the optimal maximum probability of reaching a goal from this state at tth time step. Okay, and so then P star ST is equal to 1 if S equal to G. Because if you're already in the goal state, there is no way you can do anything bad. Okay, and then P star ST equal to 0 if this is total number of time steps you have. If you're already done with all your time steps and you're in the very last time step and you're not in the goal, then the probability of reaching the goal is 0 now. Okay. Otherwise, P star ST is written in terms of the P star S with T plus 1. Okay. So basically, the probability that you did an action A in S and got into S dash, and then from S dash, you would reach the goal state. What's the maximum probability of reaching the goal state from S dash? Okay. So that's your, and so here essentially you have again a Bellman update model with max. It's completely in terms of probabilities. Okay. This we won't do. One last thing I'll do actually is say something about stochastic shortest path, which corresponds to this model. This is the one that we'll spend time. So when you're reading an FF Hop paper or the Kalabov paper, this is essentially the model they're caring about because they're thinking in terms of costs, minimization of costs. Okay, so it's also useful to think of this model as stochastic shortest path model. So this is just like A star is the shortest path model. This is the stochastic shortest path model. Okay, where notice that in the stochastic shortest path model, the reward is not associated with states, it's actually associated with SAS dash, and normally you assume CSAS dash equal to C dash A, where it's just the cost of doing action A. Unless you assume the same action can have different cost based on which state it's starting from and which state it's ending in. A simple model is to assume that costs are associated directly to the actions. So then this will just be the cost of A itself. Okay. So SSSP are a special case of MDPs where the one other interesting thing is in MDPs there is no initial state. The way I told you about MDP is, here's the world. You may be in anywhere in this world. And then you start behaving. Okay? And so MDPs don't care about what is the initial state at all. There is no notion of initial state. In SSSP, you assume a specific state is given to you as the initial state where you will start behaving. From where you start behaving. The advantage is if I tell you what the initial state is, then I can talk about prioritized sweeping. Okay, see this airy-headed thing I made earlier about in going to San Francisco, I should be focusing on what to do in the taxi stand rather than what to do in the desert. That depends on where I'm starting from. If as soon as I woke up, I suddenly find like sun, shining on me, and I see happy-looking Joshua trees around me, then I'm already in the desert. And knowing exactly what to do in the taxi stand is of no use to me at this point. Whereas, if I'm starting from here, which is my initial state, then I get to control my actions, and the likelihood that I will be in the taxi stand is higher than the likelihood that I will be under Joshua trees. So it makes more sense to know what action to do for the taxi stand. Okay, without initial state, you cannot actually talk in terms of prioritized sweeping, because initial state tells you, given where you are starting from, what is more likely to happen to you and what's less likely to happen to you. So that's one idea, again something you took for granted in planning, and for the last two classes you didn't have it. There was no initial state. MDPs don't tell you what the initial state is. But here is a special case where you assume the initial state is given. Okay? And you assume that there are absorbing states called goal states. Once you reach the goal states, you don't do any more actions. Okay? And actions have costs, all states have zero rewards, essentially. That's the stochastic shortest path MDP. Now, interestingly, this is neither finite horizon nor infinite horizon. This is what I was telling you last class. If you think in terms of stochastic shortest path, it's neither finite horizon, because I'm not just telling you that you only get to live for 85 actions. So you need to know what actions to do. How much hour time you have left to go. And it's not infinite horizon. It could be infinite horizon, but I'm not doing discounting. For example, in the model, we did not put a discount factor. Right? You don't need to. If you want, you can put it, but you don't normally need. Because normally you assume that if I do 8 actions in a plan, the cost of the plan is the summation of all the costs. It's not, first action plus beta times the cost of the next action plus beta square times the cost of the third action and so on. That's not the normal model we use when you talk about the cost of a plan. You want to add them up. So that means you want to have beta equal to 1. Normally, if it's not a finite horizon MDP, beta equal to 1 gives you technical problems. However, as I said last time, as long as there are absorbing states, and as long as you are considering cost minimization, okay, as long as you are considering cost minimization, an optimal policy has to be a proper policy. Remember this idea, what the worry that we had was in the beginning grid I showed you, people were avoiding going anywhere and just happily sitting in the middle, right? That cannot happen if all you are in the cost model, because there are no positive rewards anybody is giving. Everybody is giving negative rewards. Okay? And then the sync states are giving 0 rewards, but they just stop after that. And so, an optimal policy will be a proper policy. A proper policy is one which gives 1.0 probability, long-term probability of reaching the goal state. Okay, and so So you just have to search in the space of proper policies. Okay.